All right, we are going to be looking at linear independence, which is one of our key topics in our entire class. So let's say that you have a set of vectors, v1 to vp, and they are linearly independent if that linear combination is equal to 0, only if you have the trivial solution. So in other way, you can look at this as if ax equals b equals 0, only when x equals 0. Okay, then those are linearly independent. They can't, one term can't be written in terms of any other one. They're linearly independent, or linearly dependent if essentially there is a solution that is non-zero, because that's when we had some other examples where we had some free variables, and so x1 was related to x2 or x3, and so there's a dependency there because one of them depends on the other. Okay, so we're going to say they're linearly independent if ax equals 0, the solution to that is our 0 vector. Okay, linearly dependent if there exists a solution that is not all 0. We call this a linear dependent relationship when the weights are not all 0. The index set is linearly dependent if and only if it is not linearly independent. Okay, they're complete opposites of each other. All right, let's go ahead and look at an example here. Let v1, v2, and v3 be these vectors here and determine if they are independent. Well, let's augment this set of vectors with the 0 vector, and let's see if we end up having any solutions here. It just so happens, without doing all of the row operations, we end up getting 1, 4, 2 in the top. We get 0, -3, -3, 0, and the bottom zeroes out. So again, I didn't show you that row reduction, but this is the matrix that we end up getting. In this case, we then say -3 x2 plus -3 x3 gives me 0, or x2 equals -x3, and x1 plus 4x2 plus 2x3 equals 0, and I can plug in -x3, -4x3, making this substitution here, and so x1 minus 2x3 equals 0, and x1 equals 2x3. So these are both dependent. x1 and x2 are both dependent on x3, and so these are not going to be linearly independent solutions because I have two pieces that are dependent on x3 here. All right, suppose that we begin with a matrix A instead of a set of vectors, so just putting those vectors into a matrix. The matrix equation AX equals 0 can be written as x1, x2, all the way up to xn times your ANs equals 0. Each linear dependence relationship among the column of A corresponds to a non-trivial solution of AX equals 0 because there is that linear dependence. Okay, the relationship among the columns is this non-trivial solution because you have these x values here that are not 0, and so there's that dependency there. So the columns of A are linearly independent if AX equals 0 only has the trivial solution. So these are all very connected with each other. That's just a formal definition. So we can do the exact same thing if I needed to find out, are these columns linearly independent? So you could rename these if you wanted to, like this is A1, this is A2, this is A3. and I want to know, is AX equal to 0? So let's go ahead and augment our matrix here with our 0 vector. I'm going to go ahead and switch these two rows. Okay, -5 row 1 plus, sorry, I can't write and talk at the same time, plus row 3 is what I'm going to put into row 3. So that gives me 0, -5, -10, so -2, 5, and 0. And let's take row 2 and add that to row 3. All right, row 2 and adding that to row 3, 8 plus 5, 13. So in this case, the only number that's going to make this bottom true is x3 equal to 0. And if that's the case, then 1x2 has to be 0, so x2 has to be 0. And if that's the case, then x1 equals 0. I have the trivial solution of the 0 vector, x equals 0. Therefore, the columns of A, or these 3 column vectors, okay, if you wanted to separate them out, but the columns of A are